So let's continue. So we looked at the evolutionary algorithms, and actually the book, the Stuart and Norwick's book, actually is not very. It's kind of skeptical on evolutionary algorithms. Actually, why? Because it's kind of cool thing to do, but many times people maybe do them because it just kind of seems like kind of fun thing to do, basically, right? Searching for something, do this evolution. Sometimes it's just like overused. At least at the time, it was really being overused, right? They have their own place, right? But maybe you don't have to use them for everything, basically, right? Because you need some sort of fitness function, and again, maybe, right, the strategies, right, how you evolve, right? Again, maybe this model, this abstraction is not the best for everything. Well, obviously not, right? So now, so what kind of other search we can have, right? Basically, right? So I mentioned already that we have a continuous spaces, right? If you have continuous space like here, right, you don't really get to search for everything, right? So, right. So you can use a gradient, right? Again, I mentioned the quantization or discretization, right? You can discretize you have an infinite space, right? You can make it, one approach is to, do some chunks basically, right? Decide on some, every 0.1, every integer, maybe, convert floats to integer, only look at the integer values, for example, right? So, step size, basically, right? So here is the idea how you can find something, right? You have a function, right? Maybe let's make this bigger, right? Newton-Raphson method. Maybe some of you have heard of this method, right? Yeah, you have. Where did you hear it?
Mathematics.
They actually taught you this? Okay, that's good.
Yes.
Okay, well, it makes sense, right? So again, its idea is basically you have x2 minus 2, right? Which is what? Which is square root of 2, right? I believe in this example, right? But the idea is I believe this is how calculators do it actually. Like old ones for sure, new ones too, right? So you keep iterating and it converges very quickly. When did you learn this? First year here?
Yes.
Okay, I thought maybe like in 5th grade or something, I don't know. Right? Yeah. No, just... No. Okay, so that's good. Okay, so the idea is, of course, Newton. Well, I guess Raphson. I forget who Raphson was actually. Right, Newton. We kind of know, right? But yeah, but this method actually is used by calculators, right? The algorithm for finding roots, right? It actually works pretty well. Look at this here. After this is a real value, right? Square root of 2, right? Let me make this bigger so you can see this. Otherwise, this is let's make this bigger. We don't need this one. We don't need this. All right, and let's make this smaller. No, I can't. I guess unfortunately I can't do it. Oh, maybe. Okay, yeah. All right, it's a GIF basically. Right. So you can see that after 4 iterations, right? First approximation is 2, 1.5, right? Right. You keep going down, right? It converges very quickly. So that's the whole thing you should remember. Like after like 3, look at this. There's 4 digits, 5 digits. It's like after 4 of them, it goes down really, really quickly. Actually, like 5 iterations, you have like 12 digits of precision. So yeah, very good for finding things if you have some sort of function, right? Right. Of course, the problem is, you not always have the function, right? That's the only problem, right? So, again, we looked at it, again, those who have not taken algorithms course do not really see this, but again, as soon as you have constraints, you have multiple values, right, and you have constraints on them, right, and you want to optimize something, right, and this is usually covered by linear programming, if you have linear functions, right, linear objective, right, you can use that. Sometimes you have some sort of convex optimization, right? You have some sort of convex for finding a local optimum. But again, you don't have to worry about the actual algorithms right now. We're just trying to find out what kind of different search, domains are there. So next, a relaxation or next how should I say, subfield or a version of search is non-deterministic actions, right? So this means is you do something, but it might fail or it might do something else, right? So again, so you are like, you, for example, okay, stupid example, but let's say you roll red or black, right? You roll some dice, right? You obviously, or you roll the roulette wheel, right? So, and it might fall on a red or black, right? Or double zeros, and you lose all your money, right? So, so the same idea here, right? So you might not have a single outcome. Again, those were, you took physics, right? Yeah, right? You have the quantum physics, right? You have non-deterministic actions, right? There's just only a probability, right? Underneath, actually, that's what's happening, actually, right? So oftentimes this is actually probabilities rule actually are like the better model, right? We are not gonna do them just yet, right? But in general, like this this uncertainty, right? Not being sure what's going to happen is inherent, like in all our lives, right? Like I said, it seems like pretty certain the sun is going to rise tomorrow, right? But you're never sure. You never know. You never know, right? Yeah. So that's the thing. So, but of course, there is a way of modeling this. There could be a belief state, like different possibilities, right? The known unknowns, right? What you don't know, right? And as you gain more information, right, you might update your belief system, right? Don't, one of the things from this course, your intelligent agents to be actually rational, right? If you want to learn, right, you update. As you learn your space, your problem space, you update your model basically, right? If things, it's very non-practical, you have this idea, but it doesn't work, you have some new information, right? And you don't really use it, you just keep trying the same thing, right? So oftentimes you want to update your information, basically, and update your model, and hopefully some good things will happen, hopefully, right? So, right, so this is pretty, robotics on certain terrain, of course, always financial decision making, completely, dealing with market volatility, right? Again, you have some good information on a company, right? You want to invest in a stock, right? You have almost everything certain, but you don't know. Maybe CEO tomorrow, falls off the cliff or something. Right? There's things happening, right? So again, nothing is completely certain, right? So, right. So, vacuum cleaners. Okay, yeah. So, luckily for you, not yet, I could adjust the problem for the vacuum world. You could imagine a problem called erratic vacuum world, right? So, basically, he tries to vacuum it, right? But things might not happen as is expected, basically. Sometimes it dumps dirt, basically, right, on the floor. Right, so or maybe battery starts sparks come out, right, or things like that, right? So, right, so then you have to, of course, adjust your model. You have to assign some probabilities to these things happening, right? So again, if you think about your basic one, right, your basic vacuum from our previous chapter and from your homework, right, you can say, okay, there's always 100% probability of things happening. If you go north, right, it's 100%, you're going to go north, right? But again, you can adjust this model to say, okay, if you try to go north, maybe you will move sideways slightly. Maybe there's an error, like maybe the wheel is not well adjusted, right? There's slight probability, right? Things like that. And again, we can model this. Again, we can build a model of this as well. So you can specify these probabilities, right? And you can, of course, again, have the goal, right? So even knowing that there is this unpredictability, right? You can still work towards your goals, like cleaning the room, or I don't know, making lots of money and things like that, right? So, speaking of probabilities, this is actually one of the. It used to be one of the challenge questions on like job interviews, like for Amazon and Google and things like that. The idea being this: if you have a bad coin, right? You guys know, you have seen this, right? You have a bad coin, meaning it doesn't go 50-50, right?
Yeah, biased.
It's biased coin, right? And so what's the trick? You want, but the challenge is, but you need to use this biased coin to have what? To have a normal 50-50. How do you do it? One time?
It's always 50.
No, but okay, so here's the deal, okay. You don't know, you know this coin is bad, right? I'll make it here, right? So this is the idea, basically, this is used. So, let me make another paint job. Paint. Alright, so, and I might be forgetting, of course, the solution by now, right? But okay, you have a coin, right? Tails, it's tails, right? Right. A normal would be 50-50, but let's say you don't know, let's say you don't even know, let's say this is like, I don't know, 70, really bad, 73% and 27%, right? Right. So what do you do, right?
All in hands.
Yeah, right. It'd be nice to know, right? Your friend is right. So, so now, if I remember correctly, and maybe some of you remember this better, but it's a trick actually, right? You have, okay, this is single coin, right? So I think if I remember correctly, you do, if I remember correctly, the trick was this. You don't toss, you don't toss once, you don't toss twice, right? So you do this, so instead of head tails, you have HH, right? Tails, right? HT and TH, right? So, if you zero your basic probability, this is most likely is this, right? This is TT is less likely, but these two, right? They're equally likely to occur, right? So you basically, right? So you can treat these two as these become your 50-50. These become your 50-50 events. You just need to toss twice. Well, technically not twice. What's the problem? Well, not the problem. In this case, it could very well happen. If you get two heads in a row, right, you just toss those away, basically. Or two tails, right? So theoretically, this algorithm, it works, but it could go forever, right? If you just keep getting heads, right? It's not, if it's like 99%, like really biased coin, right? Really bad coin, right? Then you might not get the tail, you might have to wait a long time to get the tail, right? So yeah, so basically, these two are equally likely, right? HT, TH, actually, right? And those you can use for 50-50. Equally likely, basically, right? So, okay, but it's again, there are all kinds of, not nuance, but that's the idea. But again, the idea is this, that if you have some probability, right, something, you can sort of, you can adjust to it, you can add more events, there are strategies, basically, we can deal with this, right? Not perfectly, right? Not perfectly, but okay. So erratic, right? So and or search trees, right? This is this is like one of approaches, right? Basically, so if you have this is a concept when you don't have you have non-deterministic actions, right? Things could happen, basically, right? So you have some action, basically, right? On possibly, right? You branch out in these possibilities, right? You draw this and or search tree, right? This I think, I believe correctly, this should be 100%, right? I believe, right? And or search tree or road, right? There might be a success, right? On a solution basically checks that every possibility leads to success, basically, even these slightly, less likely positions or paths, right? So that's something we can use. Now, another idea, right? Yeah. So this is an interesting idea, but this is actually also kind of simple concept of try again, right? So if you are dealing in some environment and things don't always work as expected, right? You want to make a move, do something, right? You just keep trying until it works, right? So I'll show you the idea of this, right? So again, another paint. This try idea. Right. So let me draw this. Basically, right. This is kind of show you this the simple version. So there's this big tunnel, and there's this big, poor robot here, right? Poor Robbie. I don't know. It's like I don't know. It looks like a robot on Roomba or something. I don't know. Well, anyway, the point is, it has some problems, right? This robot has some problems, right? It needs to get out of this hole, right? Basically, right? It must get here, right? But it's only like, I don't know, 80% chance, right? Randomly, right? The electronics are glitchy, right? It might go up here, right? 10%, maybe 5% here, right? And 5% here, right? But in this case, this is not a problem because we have walls, right? So it will just get, nothing will happen. So you basically try again, right? And eventually, right? We don't know how many. You need to maybe make how many moves? Like again, 80%, right? 80% and 80%, right? And then we have freedom, right? Freedom, right? Freedom. Okay. Now, so at each step, of course, first step is you try and you make a move eventually, right? At some point, of course, right? You might go back, right? You might have a backwards progress, right? Because you can't, you cannot put like a stopper or something. You cannot close the valve behind you, right? So eventually, right? Of course, eventually, I hope if you have 80% chance of success, I think you will make it out, right? Right, you can make some simulations of this type of thing. Probably second homework will deal with something like this, some really unpredictable robots, basically, right? Which act like this, right? But you get the idea of this. Try again, right? Again, we do it ourselves, right? It didn't work, right? Sometimes plugging in a USB port, right? Try a couple different times, right? And eventually it works, or you break the port. Okay. Yeah. Okay. Yeah. Hope the technology is okay. So yeah, slippery one, right? So if there's some slipperiness, right? So you can also, right? But in order to work for this to work, right? Obviously, you need some sensor feedback, right? Well, usually, right? Yeah. Sometimes again, you don't need the feedback all the time. You can have here we dealt with only a couple actions, this one here, right? We just had a simple action. But sometimes you might have a cycle of actions, like a set of actions. You do a couple things, and you check maybe every 10 actions or 20 actions where you are. Because in a real world scenario, maybe you don't have the sensors where you can check immediately, get feedback, right? Like, again, self-driving car, for example, right? Again, you're getting a lot of data, but not everything. So, it's not going to be most efficient, but try again is approach you can sort of like a rule. It's like an approach you can try. try again, basically. All right. Now, for robots, like you're trying to do something, it doesn't work, the apple fell off, right? Try again. Maybe eventually, like in that game, when you're trying that, what's it called? What's the name of the game? I'm talking about the carnival game. Where you try to manipulate the arm.
Mm-hmm. Oh, claw machine.
The claw, right? You remember Toy Story, right? Right. Yeah. As you know, of course, that claw, it's not a fair game, right? It's that the sensors in that it's really weak, right? And so it seems like how hard could it be, right? But it's rigged. It's a rigged game, basically, right? So, I don't know. Anyone ever won this from the claw?
Yeah.
What's the biggest thing you won?
I think I won this is någon grov T-teater.
Mini from Minion? You got a Minion?
Yeah.
Wow, cool. Where?
It was in the USA in Orlando.
Oh, okay. That was okay. So fair. I'm thinking maybe in Latvia somewhere, right?
No.
Yeah, I was.
Not yet.
Yeah.
Definitely not.
No, okay. Okay. Yeah.
Like we're cheating for that.
Yeah. Yeah. Because I was in Disneyland in last month. I was in Disneyland, and actually I didn't want to try any of this stuff. Right. I preferred the sure thing, buying the Mickey Mouse, and so yeah. But it's fun, right? So now, so next thing again, we will cover these things more in detail later on. So search in partially observable environments, meaning you don't see the full picture, right? There's sort of say fog of war, right? Like you were playing a game, of course, right? You don't know what the other guy is doing completely, like a real-time strategy, right? You just you have some information, right? So again, this doesn't mean it's the end of the world, right? There's lots of challenges, right? If you are missing some information, right? Right? So you might only get sensors, like I mentioned, only every few moves, right? So what you do is you have to introduce a new concept, something called belief state. So how sure you are somewhere, basically. Like again, probability that I'm in the right place. I don't know yet. I'm acting like I'm in multiple places at once, basically, right? So you have to model where you could possibly be, right? Eventually, hopefully, there will be some way of verifying this. Eventually, you will observe something, right? Otherwise, of course, if you never observe anything, right? It's at some point there is, there's going to be some sort of final reckoning, right? When you fall off the cliff, right, and you die in the fire, basically, right? So, but eventually the feedback will come, right? Hopefully it will be positive feedback, right? So, again, it's going to involve some probabilities, right? Different, again, it all depends on what kind of goal. So it's going to involve building some probabilistic network, a probabilistic model, right? So, again, eventually, of course, again, there's some sensors, So again, robotic navigation, this happens all the time. Again, you'll need to adapt, right? Update your strategies depending on what's happening at some point, right? So, right on Mars, right? Actually, I haven't heard what's happening with the Mars explorers. It's been a while. Any news with the Mars exploration?
Maybe the Google's will appear, I think.
Yeah, soon. Do you think Elon will get to Mars?
Well,
He was planning to.
He was planning to.
This year.
I like him much better when he was really serious, but I hope he's still serious, right? Yeah. Before he started trolling, I mean, it's like, But okay, yeah. So, sometimes, right, you don't, right? So, you have no observations whatsoever, right? So, right. So, can you still do anything with this situation? Again, so real time, there's a really high temperature, right? You don't have sensors, don't work, right? But you have to go in, right, and do something, right? Well, it's like again, you don't get you don't have feedback, so you can still do some things, right? Assuming you can come up with a set of actions which will do it. I mean, let's say you have this, I don't know, if your eyes closed in this room, right, you know the room size, right? You just take the actions, right? And at some point you will end up in one corner if you want to get there, right? Okay, so you can come up. There are many places where this fact that there's no sensors at all, right? You can still do things actually, right? So, yeah. So it's completely challenging, right? Because the search space can be large, right? So lots of things you can do. Right, so again, you have the belief state representation, right? And what else? So making an agent for something like this, right? How would you make it? How would you make an agent? Right, this is all the things we can do. Right, you need some sort of monitoring, right? Filtering, right? You update your belief state of what's happening, right? There's things like Kalman filter, really cool thing, right? Again, estimate, right? And again, most robots, of course, the big problem is localization, where you are. So basically, you just have a probability. You are here, but you're not completely sure, right? You have sort of like little cloud around you where is probabilities where you could possibly be. It's just like GPS, by the way, right? Early GPS, right, of course, didn't have precision. Like it's like only I think 50 meters or 5 meters due to military restrictions, actually, right? But you could use other tricks. In fact, I have one of the bachelor's thesis this year. One of your colleagues from one year later, I mean earlier, is doing a thesis on localization problem for driving, on a track, right? On a racetrack, but instead of using sensors, he's using multiple phones, basically, right? And it seems pretty promising approach, actually, right? How? Yeah.
What is?
Okay. If I remember correctly, right? It's been so. Idea is this, right? Like a really cool idea. You're driving. Right. That's right. You have a racetrack. I don't know. Right. And there's a little car driving.
Like a real racetrack.
Yeah, real racetrack. This is a car, right? Right? And the challenge is to be precisely say where you are, right? Because you're doing some races and things you need to know again exactly where you are, right? So how would you solve this problem? Well, there's many ways of solving it, right?
You have a GPS.
Yeah, but the problem is GPS is not precise enough. Single GPS is not enough. Yeah, so his idea, right, is to use multiple phones based, multiple GPS, right? So again, that lets gives you more data, right? Usually more data is good, right? And you can sort of figure out probabilistically where you should be. It gives you more precise estimation, right? And this is actually how it's done in general GPS, right? You use some other source of information, right? Even if you have a bad source, like it gives you, regular GPS, I think it's like GPS plus minus 5 meters, I believe, right? I don't know, maybe less. Like you say, okay, you all have encountered the situation and you have GPS and it gives you sort of like kind of bad location, right? Not so good, like you're walking down the street or something, you're driving a car and it sort of like jumps around a little bit, right? So that's what's happening, right? GPS is sort of like when it works, it seems like, okay, it's amazing, right? But it's actually, there's lots of this, adjustments happening behind the scenes to give you this really good localization. One of the tricks they use, when I say, I mean Google, right? Is Wi-Fi, right? You have Wi-Fi, it has a network of Wi-Fi signals around the city where it supposedly knows where each signal is, right? That can help locate you, right? Yeah, gives you a good location, which could be a good or bad thing, right? So depends what happens if you're trying to hide, right? Right. So that's why they also, you have encountered this, like it says, turn on Wi-Fi for better localization. It doesn't say localization, it says something else, but something like that. For better, what's the word? For better, precision or something like that. Right. Okay, so the same approach here, right? You could buy there's some really expensive sensors, right? And then, these really expensive sensors, this like a couple $1,000, you could have it, for professional racing cars, they have them, right? But if you're doing amateur racing, you don't have it, you don't really want to spend a couple $1,000 in sensors, right? But getting a couple buddies' phones together, right? That's a viable approach, right? And again, you have multiple phones, right? So multiple phones here. You put a phone here, put a phone here, put a phone here, put a phone here. No, not like this, but even a couple, right? Different data sources, and you can get a better estimate, right? Okay, so just one of the things, I'm kind of sketching out what's possible, right? Yeah. That the fact that there are problems, right? That there's nothing is completely sure, in the real world doesn't mean we can't do anything, right? So we can still make progress, right? Right. So this is the problem of localization, right? Again, you send in a robot and it builds, builds a 3D model of your building, right? Again, so finally, I think this is the final thing, or not yet, but one more thing is online search, right? Meaning updated data. Offline, you get all the information and you know what to do, right? You figure out the strategy first, right? Online means that data keeps updating, right? New information comes in, right? So you have your initial knowledge, right? You have some plan, right? But you have to update this, right? New stuff comes in all the time, right? And of course, you by definition you don't have full information because new stuff is coming in, right? So let's see, mapping problem, right? So again, in online search, you're navigating something, right? You need to build your world, your environment, based on incomplete information, just like the tracing run, right? You have a basically, you know, you send in a robot in a room where nothing, you don't know about anything but the room. You have to build this world, right? So making this decision, right? You have to just make decision what to achieve some goal, right? Whether to, you know, I don't know, gather something or move something, right? So there is a sort of like a challenge of explore or exploit, right? Exploit seems like a dirty word, exploitation, but in AI, this means doing something, you know, productive actually, right? Exploration is like you're trying to learn something, right? So again, I'll use a driving car, of course, right? Exploitation would be driving something, right? Driving somewhere, right? Exploration would be actually learning, you know, using sensors to learn something, right? So sometimes, you know, you need to actually, in order to do something, you first need to explore like the surrounding space, right? You need surrounding space, and only then you can actually do something productive, right? So my last year's project dealt with this, with exploration, exploitation, you know, dilemma or challenge, right? How much do you explore before you exploit, right? Sometimes you can do both, right? So exploitation, right? Exploitation means achieving goals, right? So basically any, you know, pretty much all real world models will deal with online search because things will be updated, right? Yeah. So let's see. You may also get the dead end, of course, right? Also, I think this is probably going to be next week. We'll do more with adversary, right? Maybe there could be also some challenges, right? Some adversaries, right? We have not really talked about those yet, right? Things which prevent you from reaching goal, actively working against you, right? So if two-player games, of course, there's other player is working against you, right? It's not a cooperative game, right? So for now, we just have a single agent nicely working towards the goal, you know, right? So no other player characters or NPCs, just one single NPC, right, exploring the world, right? So, right, so of course, so again, another concept, safe exploration, right? Whether there's danger. Are you going to fall off the cliff, right? Can you explore without blowing up, right? So again, so all depends. So oh yeah. Oh, this was I mentioned this video, right? You may have seen this one, right? This is somebody really didn't think too much about his plan, right? You can watch this later, right? But he actually managed to reverse, right? I don't know how he managed to reverse on this road somewhere in China, somewhere, right? So yeah. So basically, again, getting stuck, right, might not be the end of the world, right? So, but yeah, I don't know. So, what else? So, balance, exploration, exploitation, right? Pretty much everywhere, right? Online, local search, right? Real life, right? Making the sequential decisions in real time, right? And we keep getting feedback of what's happening, what's going on, what's working, what's not working, right? So, random walk strategy, right? You might have heard of random walk or Brownian motion, right? You have to make a choice. So what do? You just toss a coin or toss or right? It might not be optimal, most likely it's not going to be optimal, but it can be surprisingly effective, right? So sometimes, again, your structured search might get stuck on some loop, some sort of like, keep doing over, some randomness, right? Sort of like to move things around, to shake things up basically, right? You shake the structure up on the random walk actually might work very well actually, right? So, yeah, learning real time A-star, right? Might be that updates. There's A-star algorithm, a very nice algorithm on which actually updates information. Very, very nice one. So learning, again, of course, in online search, there is going to be a learning. And what else I want to talk about? Okay, this is all already notes. Yeah, like 10 minutes, but I think I had some, we'll do some little hill climbing algorithm afterwards. Okay, yeah. So, search, again, it's a fundamental way we solve problems in AI, right? We need some sequence of actions to lead to the goal, right? But, again, most real life problems, of course, are going to need some, there's going to be probabilities, we will not have all the information. Also, some information may be coming in, right? So, we can classify or search algorithms between, discrete or continuous, right? What can we do? Deterministic or non-deterministic, meaning, are we sure this is going to work or not? And also, do we know everything about the world? Or is it partially observable, right? So, let's do a simple simple hill climbing algorithm. Really simple. Okay. This is going to be our function, x squared plus 3x plus 5. Obviously, if you're doing some math analysis, you could figure out the maximum yourself. You do the derivative, right? You could figure out, right? But, oh, come on, what the heck? Right? But, unfortunately, in real life, you don't have the function. You have some really weird function. You can't really calculate the maximum like that, right? You need this, basically, then. So, I remember this is like 12th or 11th grade, right? Finding maximum.
I think this, I should take a look at it again, but
Yeah.
there's no maximum.
To me?
It has no maximum.
Let's take a look. Could have minimum, right? Could have because it's parabola, right? Right? So only minimum. Yeah? Good point, right? And that's possible. It's okay. No, I put negative. That's why I did it. I put negative. Yep. Yeah, it's negative here. Yeah. Okay. But don't look at the comments. Look at the code, right? Comments don't follow the code. Yeah. And the problem, of course, is. Yeah, the problem is that's the problem, right? That comments might not, and then you have a problem whether the comment is right or the code is right. Right? That's a real life problem, especially if you're dealing with your somebody else's code, or even worse, your own code from like 2 years ago, right? You don't remember which one was the correct version, right? So we have randomness mass, right? So this is a function, right? We can come up with a new one, right? For now, it's really simple, right? And I kept so find best neighbor, step size, best neighbor, right? We check, minus. We check both, we check both neighbors. So we check both. We check in both directions, right? Right, obviously, right? Uncheck, right? And that's when we keep going. Best neighbor value, right? It's so simple, right? On hill climbing, now, okay, iterations, step size, debug false, minimum improvement. So you set a threshold, right? You again, due to the way how floats work, right? You might eventually, stop, right? So let's see how quickly do we get there. Let's run this function. Connecting the kernel. So one is start, right? Where we start, right? Step size 0.1. Right, so this will get to 1.4, I think 1.4 was the max, right? I believe. Or is it? No, 1.5. 1.5 is the max, right? You already solved this? You Googled. Oh, Wolfram will get you the max, right? Yeah, because, yeah, actually I did myself too, right? I did the derivation, right? So, minus 2x, you solve it, yeah, 1.5. Yeah, you can solve the derivative and that will give you 1.5. But again, but the problem is that not everything is derivable like this easily, right? So, yeah, your function might be much harder, right? So very simple idea, right? This code, right? Doing your own hill climbing, right? Again, you just change the steps, change the function, right? And again, in this case, it's in a, you know, since we only have single x, you know, variable, right? Linear space, right? But possibly you might need to explore in multiple dimensions, right? In a two-dimension, your vacuum cleaner will have 2 dimensions, right? So in 4 directions, right? To explore, right? So, okay. So this code, can we try something? Let's try something else. Like let's try, I would like to make this, how could I make this more functional? I could pass in well, I can pass objective function. Oh yeah, here. Right. I could make this hill climbing, right? Let's make this, I'll update this. You know what I'll do is, I'll give a function, right? Since functional language, I'll pass the function. Obj function, right? Okay. Yeah. I'll put it here. Fun. Objective function, right? So what I'll do is, object fun, right? Yeah, like this, right? Yeah. Yeah, object old value on find best neighbor. Again, but it also needs this function, right? Objective function. Right? And I will pass it through, right? Find best neighbor, objective function. Let's see if this works, right? Yeah, I think it will work, right? So now, why did I do this? Because so I can pass any function to this hill climbing, right? I can find it for any function, right? So here it will work. Let's try this. Hopefully it will work. Okay, now it should work. I can put a lambda function. Now let's pass in a different function. Let's say no, something else like fx. Give me a function.
Minus x to the power of 3.
Okay. Plus.
This looks good.
Okay. Let's see what happens. So, no, we could do this. Yeah, this is one way of doing, right? Yeah. Now, but I'll do this different. I'll call it 2, right? So objective. So this is a test. Will this work? Yeah. Yeah. This should work, right? Yeah. Iterations, right? X is 1, right? Objective fun, or object. How do they call it? Object fun, right? Yeah, like this. Let's see if this works. Well, it will work, but of course, we're depending on where we start, right? Let's see if it's actually how well do we do. Okay, 1.1. It got up to 1.1. So that's the maximum. Really? Interesting. Why did it? There's something kind of iffy. Right? Is that actually correct? 1.1? No. Doesn't sound right. No, I don't say this is a maximum. It's because what we did iterate. Why did it only do 1, 0 iterations? Why did it stop? because it is not making any progress, right? I think that's a problem. Yeah, so let's try this 10. Whoa, you see? It started moving, right? It started moving and it went down, right? It went down, it got to 7.5. Is this the maximum? No, it's only because I had 25. Let's do 125 iterations, right? Right? And it will keep going, right? It will eventually get to 4.3. Very interesting, right? It stopped 1.3. So what's the true value? You have to derive, right? And solve the quadratic, right? Right?
Yeah, you know, it's,
Did you do a graphing?
yeah, the graph.
What's the actual?
It has maximum and minimum.
Yeah, it has max and min.
Yeah.
But wait, isn't it like kind of like this?
Yeah, well, it has like, it like goes from minus infinity.
Yeah. So again, that shows only this. In this particular case, we start it where you end up is dependent on where you start, right? So here we start at 10, right? We find local minimum within this area, basically, right?
So what did it find?
It went down to 4.4, right? Right?
4.4 is actually root.
Oh,
Yeah.
okay. Very interesting. Very interesting. Okay. So yeah. So again, so takeaway from this, we'll stop with okay. So stop. So takeaway from hill climbing implementation. Where you end up depends on where you start, right? You will find some local minimum or maximum, right? But this, because remember, we have the problem of 0.1, right? We are not doing simulated annealing, we are doing just set steps. To make it, we could adjust this to make it sort of jump more in the beginning, right? And then settle down, right? Some simple implementations. Okay. Yeah. Yeah. Okay, any questions? No? So see you on Monday. On what we're going to talk on Monday, I'm going to check on adversarial. So on Monday we'll look at enemies. So things that fight against you.